Hi, hello. Welcome to this channel. I am Divya again. So in this video, we'll talk about finding out the stress values and strains in bars of varying cross sections. Okay. In the last video, we talked about finding out the stresses and strain values for prismatic bars, which is of which will have the same cross section like this, right? So if we take this type of bar, either circular or any other cross section, if it is a circular bar and it is subjected to some external force amount of P, and this P could be any value, could be 100 kilonewton or 1000 kilonewton. So and this the diameter of the rod is D, right? And we know how to find out the stress value. The stress, if we take the stress as sigma is equal to load divided by area perpendicular to the load. So this is the area perpendicular to the load, right? And this area that we need to consider, right? So this area can be named as A. So this is the stress formula. So now what if the cross section of the bar is varying from point to point like this, right? Suppose we have some bar, right? We have bar like this, um, a bar like this, and we have another bar, right? We have sorry. And we have another bar like this, and we have one more bar which is of even smaller than this section. Section like this, right? And this bar is subjected to force, some external force P, right? So this whole section is subjected to some external force P. Suppose the cross section area of this bar 1, suppose we name this bar as first bar and second bar, and this one is third bar, right? And area of this first bar is A1, and area of this bar is A2, and area of this bar is A3. So how can we calculate the stress value in all the three sections, right? Okay. And we have the question that if the stress varies from section to section, from material, from first portion to second portion, we want to know if the stress value varies, right? Absolutely, the stress value will vary from section to section, because from this equation we can see the stress value depends upon the type of load, amount of load, and the cross sectional area, value of the cross sectional area. If the value of cross sectional area, the stress is indirectly proportional to the area of the cross section. If the cross section area decreases, stress value increases, right? If the cross section value decreases, then the stress value become increases, right? So there is a relationship between the stress value and the cross section of the element, right? So this A1 portion has larger cross sectional value, so the stress values induced here sigma 1 will be lesser than other two sections, right? And the stress value induced in the part 2 second portion is sigma 2, and here is sigma 3. Now we have to calculate the stress value sigma 1, sigma 2, sigma 3. How can we calculate? All the three portions are subjected to same amount of load, which is P, right? So sigma 1 is equal to load divided by cross sectional area. So what is the cross sectional area here? A1, right? And sigma 2 is the load divided by area. Load is P and area here is A2, right? And sigma 3 is equal to load divided by area. Load divided by area is A3, right? So now these are the stress values. Now if we know the values of P and the cross sectional area or the diameter or size of this portion, we can calculate the area, and we can substitute here and we can calculate sigma values, the stress values, sigma 1 and 2 and 3, right? Okay, because we want to know the extension of these rods. Since this material, this element is subjected to tensile load, so obviously the cross section elongates, right? Okay, how much length it elongates, that we want to know, right? So what is this sigma how can we calculate strain formula? What is the strain formula? We can take the strain formula from Young's modulus, right? So Young's modulus is equal to stress divided by strain, right? Again, strain is equal to stress divided by Young's modulus. Again, the stress can be written as change in length divided by original length, which is equal to sigma divided by E. And the sigma can be written as P by A, right? So P by AE. So this term AE can be called as axial rigidity. Axial rigidity. Now I can rearrange this equation as del L is equal to PL divided by AE, right? So I can calculate, this is the change in length formula for any type of cross section, whether it is a circular or square or rectangular. For any type of cross section, this is the general formula, right? So change in length is equal to PL by AE. So AE represents axial rigidity, A represents area, E represents Young's modulus, P represents amount of load applied, L is the length of the portion, right, under consideration. Okay, now if we have to since the cross section of the material varies from point to point, right, this is from A to B, there is where some cross section, and from point to B to C there is some other cross section, and the cross section varies from C to D also, right? So each portion, as the stress varies from portion to portion, the stress elongation also varies, right? So how can we calculate the elongation, right? So elongation for the portion 1 can be taken as del L1, right? Del L1. So del L1 is equal to P is the load. All the three sections are applied to the same amount of load. So P, and the length, consider the length of this portion is L1, and the length of the second portion is L2, and length of the third portion is L3, right? So the length of the first portion is L1 divided by area of the first portion is A1, and I am considering all the three portions are made up of same material. So same material is, Young's modulus is same for all three sections, right? So here E. Likewise, I can write the equation for another two portions. So P, length is L2 divided by A2 E, and for del L3, right, del L3 equal to P L3 divided by A3 E, right? So I want to calculate the total elongation. These are the formulas to calculate the elongation of each portion, right, separately. So I want to calculate the total elongation. What I can do, the total elongation can be written as del L. So total elongation is the sum of elongation of separate each portion, right? So del L1 plus del L2 plus del L3, right? Okay. So this is the total elongation, and we know if we know the values of all the parameters, which are load, length, area, and Young's modulus values, we can substitute and calculate del L1, del L2, del L3, and substitute sum it up to get the total elongation because of the applied load. So this is how we can solve bars of varying cross sections, right? Okay, thank you. We'll solve a problem on this model in the next video. Thank you.